Hello everyone, and welcome to the first video for Chapter 9, which really looks at the basics of conic sections. So in this video, our skill objectives are number 1, learn the name of each conic section. Number 2, define the different conic sections. And number 3, recognizing the algebraic equation associated with each conic section. The conceptual objectives are number 1, understand each conic as an intersection of a plane and a cone, and number 2, understand how the equations of a conic are related to the general form of that second degree quadratic equation. The first thing we really need to discuss is exactly what is a conic. Well, a conic section is really a curve that results when a plane intersects a double cone. Now this right here is what we mean by a double cone. You have a cone on the bottom and a cone on top. And what's going to happen is that a plane is going to intersect this double cone by intersecting at various angles. So if that plane, like in this first one here, we'll get a circle if the plane is parallel to the base of the cone. So when it goes through there, imagine that this double cone, it's like an ice cream cone, so it's hollow inside. So when that plane intersects the cone, you're just going to get that set of points right there, which is a circle. If we tilt that plane a little bit, so what happens now, the plane is going to go through the two sides of one of the cones, either the bottom cone or the top. In that situation, like in this one right here, we'll get an oval, or what's actually called an ellipse. If that plane tilts even further, so what happens then is it's going to go through the side and the base of the double cone. In that situation, what we're going to get is a parabola. And this is the first time you've actually seen a more formal definition of a parabola, which we'll look at in a little bit. And the last one we have is when that plane is tilted at such an angle that it intersects the top and bottom cone, in which case you get the only conic that actually is in two pieces. You get the hyperbola. And the other thing you have to keep in mind, we are going to go and formally define each of these. So the working definition that you've had in the past, that a parabola is a U-shaped graph, is not necessarily going to hold anymore. What a parabola is much more specific. The circle is the very first conic, and we really don't define that circle because we're familiar with that definition. A circle is just a set of points that's equidistant from that fixed point, which is the center of the circle. Now with these other conics, you're going to have, it's all related to distances in some way. So what we have here, the first conic that I want to really formally define is a parabola. A parabola is the set of all points equidistant from a fixed point, which is called the focus, and a fixed line, the directrix. So in this picture that we have here, this line right down here, that would be the directrix. This point right here is the focus. Every point that would be on this parabola, on that red graph, is going to have a distance from that focus and a distance from that directrix. And what happens, every point that's on this graph, the distance from the focus, from that point to the focus, and the distance from that point to the directrix will always be the same. The second conic that we want to go through and define is what's called the ellipse. Now, an ellipse is similar to a circle. In fact, one of the things we can say is that every circle is an ellipse if it's tweaked a little bit. And I'll explain that in a second. By definition, an ellipse is the set of all points, the sum of whose distances from two fixed points, called the foci or foci, is constant. Okay, so here we have our two fixed points in red. If I take any point that's on the graph of the ellipse, I go through and find the distance from that point, from the point on the ellipse to each of the fixed points. If I add those distances, I will always get the same thing. So in this case, the distance from the blue point to the two red points are D1 and D2. And the distance from the green point to the two fixed red points are D3 and D4. So in this case, D1 plus D2 will always equal D3 plus D4. Now, how is a circle an ellipse? Because a circle doesn't have the two fixed points. It has one fixed point. Well, really what happens with a circle is that it's in essence, you can think of it as an ellipse where the two fixed points are now on top of each other, is really what's happening there. As these two fixed points move closer and closer together, as they move closer together, you're going to get something that appears more circular. The last of the four conics that we want to define is what's called the hyperbola. And really the hyperbola definition is very similar to the ellipse definition, it just changes one word. A hyperbola is the set of all points, the difference, there's the change, the difference of whose distances from two fixed points is constant. So again, we have our two fixed points right here, and those fixed points again are called foci or foci. And there is, for this blue point, there is a distance from that blue point to each of the fixed points. That first distance is D1, then we have D2. And then if I look at the distance, if I take the green point, the distance from the green point to each one of the two fixed points is D3 and D4. And with a hyperbola, if I take the difference of those distances, that will always equal the difference of the distances of the two of any other point that is on the hyperbola. So in this case, and notice we're using absolute value because you can't necessarily guarantee which one of those is bigger, which one is smaller. So the absolute value of D2 minus D1 will always be equal to the absolute value of D4 minus D3. And that is what makes a hyperbola. Now we get to the general second degree equation. The general second degree equation is ax squared plus bxy plus cy squared plus dx plus ey plus f, where a, b, c, d, e, and f happen to be real numbers. And what happens on this? Everything here, any equation, I put any real numbers into in for those six constants, I will generate one of the conics. Okay, now there are some what are called degenerate conics, and we'll talk about those later on. But what you have with this, whenever you have one of these equations, you do have one of the conics. Now, to classify that conic, what we're going to do is I want you to remember the quadratic formula. And specifically, I want you to remember what was underneath the square root in the quadratic formula. That was called the discriminant. And when you're working on these ones, with the discriminant in that quadratic formula, we use that to determine what type of zeros we would have for that particular quadratic. Well, in this situation here, we're going to use something very similar to that discriminant. It is still going to be b squared minus 4ac. Okay, so we're going to still be using that b squared minus 4ac. But now the a, b, and c are these particular constants up here. A is the coefficient on x squared, b is the coefficient on x times y, and c will be the coefficient of y squared. And what happens then is we will evaluate that. And if that comes out to be a negative number, then we're dealing with an ellipse. If this thing equals 0, then it's a parabola. And if this thing is greater than 0, if it's a positive number, then it's going to be a hyperbola. And that's really what you're going to be looking at on these problems. So you're going to be you're going to be given an equation, a general second degree equation, and you're going to be asked to classify if you're looking at an ellipse, a parabola, or a hyperbola. Let's take a look at a couple examples. In example 1, what we have is 2x squared plus y squared equals 4. In this example, a is 2, b is 0, and c is 1. So if I evaluate the discriminants b squared minus 4 times a times c, I get 0 squared minus 4 times 2 times 1, which gives me negative 8. Since negative 8 is less than 0, I know that this equation right here represents an ellipse. Another thing they can do, you'll look here, number 2, example 2 is very similar to example 1. It looks the same, except notice that y squared now is to the right of the equal sign. So what I'm going to do is subtract y squared. So 2x squared equals y squared plus 4 is going to become 2x squared minus y squared equals 4. Now in this situation, a is 2, b is still 0, but now c is negative 1. And then when I evaluate that discriminant, because c is now a negative number, it's going to come out to be a positive 8. Positive 8 is greater than 0, so I know number 2 represents a hyperbola. Let's look at this one right here. X squared plus 2xy plus y squared minus 3x plus 2 equals 0. Okay. In this one, a is 1, b is equal to 2, and c is 1. So plugging it into that discriminant, b squared minus 4 times a times c becomes 2 squared minus 4 times 1, which will be 4 minus 4, which equals 0. Therefore, this particular equation represents a parabola. The last one is an interesting one because of what we're looking at. X squared plus y squared equals 25. Right away, you should recognize that as the equation of a circle with a radius of 5. But again, remember what we said is that that a circle is a special case of an ellipse. And you'll notice in this, a is 1, b is 0, c is 1. And so I get 0 squared minus 4 times 1 will equal negative 4. So in this case, that classifies as an ellipse. But in reality, we do know that this is a circle. Now, this does now conclude the video for 9.1. Just make sure you have the whole idea of the discriminant down. And in the next couple videos, we will define each one of the conics, the parabola, the ellipse, and the hyperbola. We'll more formally define them. And we'll also be looking at some of the properties of them because they all have some very unique properties that really affect how we live our lives today.